In the previous class, we have studied about particulate arrangement in coarse grained and fine grained soils and about loose and dense matrix of sand deposits and forces between the clay mineral particles and their structural arrangement. So, in this lecture, we will be learning about the index properties and soil classification systems. Basically, we will try to get the index properties of soil, both coarse grained soils and fine grained soils, in order to classify the soil or to group the soil. So, these index properties, they refers to those properties of the soil that indicate the type and condition of the soil and provide a relationship to the structural properties such as the strength and compressibility or tendency for swelling, that is increase in volume, or permeability, the ability to drain the water. So, index properties refers to those properties of soil that indicate the type and condition of the soil and provide a relationship to structural properties such as strength and compressibility or tendency for swelling or permeability. Basically, these index properties can be divided into two categories. They are soil grain properties and soil aggregate properties. So, here as we have seen, the soil index properties are divided into two major categories. They are soil grain properties and soil aggregate properties. So, the development of the ability to think of soils in terms of numerical values of their index properties should be one of the foremost aims of every engineer who deals with soil mechanics. The development of the ability to think of soils, basically the soil properties, in terms of numerical values of their index properties should be one of the foremost aims of every engineer who deals with the soil mechanics. Now, let us look into the type of the properties which come under soil grain properties. The soil grain properties are the properties of the individual particles of which the soil is composed without reference to the manner in which these particles are arranged in a soil mass. For example, mineralogical composition, specific gravity of the solids, size and shape of the grains, they form the example of soil grain properties. So, the soil grain properties are the properties of the individual particles of which the soil is composed without reference to the manner in which these particles are arranged in a soil mass. So, example under this category are mineralogical composition of a soil, specific gravity of the solids, size and shape of the grains. Coming to the soil aggregate properties, in this slide we will try to understand about the soil aggregate properties. The soil aggregate properties are the properties which are dependent on the soil mass as a whole and thus represents the collective behavior of the soil. So, if you look into here, the soil aggregate properties are dependent on the soil mass as a whole and thus represent the collective behavior of the soil. So, soil aggregate properties are a function of stress history, mode of soil formation and the soil structure, that is arrangement of the soil particles and mode of soil formation and the stress history, that is the type of the stresses the soil being subjected. Here in this soil aggregate properties, aggregate refers to the soil itself. It may differ in porosity, relative density and water and air content and consistency. So, soil aggregate properties which are basically depend on the soil mass as a whole and thus represent the collective behavior of the soil. Basically, it is a function of stress history, mode of soil formation and soil particular arrangement. Out of soil grain properties and soil aggregate properties, soil grain properties are widely used. So, although soil grain properties are commonly used for identification purposes, the engineer should realize that the soil aggregate properties have a greater influence on the engineering behavior of the soil, because most of the engineering structures are founded on the natural deposits or undisturbed soil mass. So, although the soil grain properties are commonly used for identification purposes, the engineer should realize that the soil aggregate properties have a greater influence on the engineering behavior of the soil. because the most of the engineering structures are founded on the natural deposits or undisturbed soil mass. So, in this slide we look about the index properties, different types of index properties. They are basically divided into two major categories. One is grain size distribution and consistency limits. Under grain size distribution, there is a mechanical analysis and hydrometer analysis depending upon the size of the grains of soil, and under mechanical analysis another category which is subdivided into a dry method of analysis and wet method of analysis. Hydrometer analysis is generally used for fine grained soils. Mechanical analysis, or which is also known as sieve analysis, which is used for determining the gradation of coarse grained soil particles. The second part, that is basically these consistency limits are meant for fine grained soils. Basically we tend to determine the various physical states of water, physical states of soil with water, like liquid limit, plastic limit, plasticity index and shrinkage limit. These are basically for fine grained soils. Once we have these index properties in terms of the numerical values, it will be possible for us to classify the soils or classify or group them with identical index properties. So, in this lecture what we will be looking is to understand the grain size distribution and what are the different methods available for determining the gradation of the coarse grained particles as well as fine grained particles. So, in the next lecture under part 2 we will be seeing the index properties of fine grained soils, and we will try to classify the soil based on the index properties obtained from the grain size distribution of the soil as well as from the consistency limits. So, let us look into this grain size distribution. So, in soil mechanics it is virtually always useful to quantify the size of the grains in a type of soil. Since a given soil will often be made up of grains of many different sizes, and sizes are measured in terms of grain size distributions. So, GSD, that is grain size distribution, assists in providing rough estimate of the soil engineering properties. So, once we know that GSD, then we will be able to guess the rough engineering properties of soil. So, in soil mechanics it is virtually always useful to quantify the size of the grains in a type of soil, and since a given soil mass will often be made up of grains of many different sizes, varying from very fine particles to large particles, and sizes are measured in terms of grain size distribution, and GSD assists in providing rough estimates of the soil engineering properties. So, here if you look into this, nowadays a subject of active research interest today is the accurate prediction of soil properties based on grain size distributions at void ratio or soil particle characteristics. So, now there is a active research is going on in the arena of soil mechanics today is to accurate prediction of soil properties based largely on the GSD's, grain size distribution curves. So, when measuring the grain size distributions of the for soils, two methods are generally used. For grains larger than 75 micron or 0.075 mm, sieving analysis or mechanical analysis is used. For grains in the range of 0.075 mm to finer than 0.5 micrometer, that is for grains less than 0.075 mm, the hydrometer analysis or which is based on the sedimentation analysis is used. So, for grains larger than 75 micron, sieve analysis is used. For grains in the range of 75 micron to 5 micron, the hydrometer analysis is used. For grains in the range of, for the grains less than 75 micron, the hydrometer analysis is used. So, let us look into the procedure of the sieve analysis, which is basically used for coarse grain soils, the particles greater than 75 micron or 0.075 mm. So, a sieve analysis is a laboratory test that measures the grain size distribution of a soil passing it through a series of sieves. So, it is nothing but a stack of sieves of different sizes. This can be a sieve of size of 4.75 mm and this can be a sieve of size of 75 micron. This can be a sieve of 19 mm and this can be a sieve of 75 micron. So, once the soil mass of known weight is placed on the sieves, and when it is subjected to shaking in the horizontal direction like this is shown here, then the amount of the soil particles which are retained in each sieve indicates that the particles are larger than the particular size are retained in that particular sieve. So, each sieve has got a different sizes representing the equivalent diameters of the particles. So, it is a screening process in which coarse fractions of soils are separated by means of series of sieves. Here you can see this particular portion of the soil which is actually passed through these two sieves and collected here, and this is the portion of the soil which indicates the portion which is passing through this particular sieve which is above this. This indicates that the particles which are passing through this sieve are finer than the particles which are the sieve sizes which are lying above. So, with this method what we do is that we segregate the soil into different compositions of equivalent diameter of the particles to determine the grain size distribution. So, in this slide what we look is different sieves of sizes are given, and this is I is equal to 1 indicates a 3 inch sieve and I is equal to 2 indicates 1/5 inch sieve. That indicates that 3 inch is a sieve or a mesh size, a square mesh size, up to the large number sieves up to around up to 4.75 mm. The sieve number is indicated by the size of the mesh itself, that is up to 4.75 mm. You can see here 0.375 inches is the sieve number, and also the particle diameter equivalent is also 0.375 inches. So, this is in the range of the gravels, and from 4.75 mm onwards to 75 micron size, the sieve numbers are indicated, categorized like number 4, number 6, number 20, number 100, number 200. Number 200 indicates the sieve number for 75 micron particle size 75 micron soil with 75 micron size. So, larger sieves are indicating by the opening sizes. For example, here number 8 sieve indicates that number of holes per inch are 8, that means that number of 64 holes will be there in a square inch. So, size of the hole or a size of the mesh will be less than this 1/8 of the inch, because there will be the width of the wire will be coming to the picture. So, here we see in the sieve analysis what you have seen is that a stack of the sieves with a varying number of sizes to segregate the particles ranging from 3 inch to 0.053 mm size. So, with this what will happen is that we will be able to segregate gravels, sands and fines which includes silt and clays. So, in this slide what we see is a mesh with the opening size which is indicated by a sieve size, which gives particle size of D, which represents the equivalent diameter. Basically, the soil particle cannot be of any regular shape, it can be of any shape, but finally it gives which is in terms of the equivalent mesh size of the sieve. So, the procedure involved for the sieve analysis of soils is you have to take the oven dried soil mass M0 in the top sieve, and shake and agitate the stack of the sieves until the soil grains are retained on the finest size sieve through which they can possibly pass. So, weight of the mass of the soil M1 Mi retained on each sieve has to be determined. So, that is what we take is that we will be taking oven dried soil mass M0 into the top sieve of the stack and shake and agitate the stack of sieves until all soil grains are retained on the finest size sieve through which they can possibly pass, and weight the mass of the soil Mi retained on each sieve. So, for each sieve size used, compute Ni, that is percentage finer, that is percentage by mass of the soil sample that is finer than the ith sieve size. For example, Ni is equal to 1 by m naught sigma j is equal to I plus 1 to n, that is mj into 100%, which is equivalent to 1 minus sigma j is equal to 1 to I mj by m naught into 100%. And once we get this percentage finer, when we plot with the particle size on the semi-logarithmic paper, then we will get the grain size distribution curve. So, the procedure involves taking a dry mass of soil and place in a sieve shaker and subjected to shaking for about 10 minutes, so that the particles are agitated and separated and segregated into number of sieves, and collect the mass of the soil which is retained in each sieve. And once we get the weight of the mass of the soil which is retained in each sieve and determine the percentage finer. Once the percentage finer is determined, plot this percentage finer on the y axis with grain size or the particle size on the x axis on the logarithmic scale to get a grain size distribution curve. For example, let us assume that we have taken a dry soil of 500 grams in weight, 500 grams in weight. Let us assume that we are having a sieves like 4.75 to 1 mm and 425 micron, 212 micron and 150 and 75 micron. Let us assume the grain diameters are equivalent to the sieve numbers here in the form of 4.75, 2 and 1 up to 1 mm sieve. Then 425 micron sieve, that is 0.425 mm, 212 represents grain diameter of 0.212 mm, and 150 is 0.15 and 75 micron is 0.075 mm. Once after subjected to shaking, let us say that this is the weights which are retained in the each sieve. For example, 4.75 mm sieve, the soil retained is 10 grams out of 500 grams. That indicates that 490 grams of the soil, weight of the soil is passed through this particular sieve. Similarly, determine the weight of the soil retained in the sieve number 2. Similarly, determine through all the sieves. So, next step is that determine the cumulative weight of the cumulative weight. So, once we get the cumulative weight of the passing, that is nothing but this is total weight of the soil mass taken in the analysis 500 grams. So, 500 minus 10, that is the cumulative weight is 490 grams. So, 500 minus 175 is 325. Similarly, 500 minus 440 60 and 500 minus 480 20 grams. Determine now the percentage finer is nothing but cumulative weight of the passing to the original weight of the soil which is taken, that is 500 grams into 100, which gives us 98%, 65% and 45, 28 and 16, 12 and 4. This indicates that 98% of the particles are finer than this 4.75 mm size. That means that only 2% of the particles are coarser than this particular size. So, once we get the percentage finer and grain diameter, we can get the grain size distribution curve. So, once we have this distribution, then we can determine the gradation like this. We have seen in the previous example that only the 20 grams of the soil which is passed through 75 micron sieve. So, this gives us the percentage gravel in a soil matrix which is greater than 4.75 mm is 100 minus 98 is 2%. That is 2% of the soil mass which has been taken represents a gravel size particles. Percentage coarse sand, again that is in the range of 4.75 to 2 mm, represents 33%. percentage medium sand represents 2 to 0.425, represents 65 minus 28 now 37%. So, percentage fine sand represents 28 minus 4 24%, and percentage silt clay fraction, that is passing through 75 micron sieve, is we have only registered about 20 grams, that indicates that 4%. Suppose if the weight of the soil mass which is passing through silt and clay particles, if the percentage of the silt and clay fraction passing through 75 micron is say less than the 12%, then the hydrometer analysis or wet mechanical method of analysis is not required, that is the sedimentation analysis is not required. But if the percentage of silt fraction is greater than 12%, then it is required for us to to determine the fine grained fraction size to assess the hydrometer, to assess the percentage of the clay particles and percent of the silt particles. So, that will be, that can be determined by hydrometer analysis. So, what we studied is to plot, segregate the soil particles and get percentage gravel and percentage sand and percentage clay. Once the percentage is found to be that is fines percentage, if found to be less than 12%, then we said that the hydrometer analysis or further fine grain analysis is not required. If it is found to be more than 12%, then we are required to do the fine grain analysis, which is generally based on the sedimentation analysis is carried out. So, from the based on the previous discussion, if you look, we can plot the typical grain size distribution curve like this: percentage finer by weight on the percentage finer by weight on the y axis, particle diameter or the grain diameter on the logarithmic scale. So, here you can see the particles can vary from 10 mm or greater than 10 mm up to 0.01 or less than 0.01 mm. All these particles can be represented on a semi-logarithmic curve like this. So, this is the decreasing particle size can be seen in this direction from left to right. So, the ratio of particle size distribution from the largest to the smallest in the soil can be greater than 10 to the power of 4 times. That is, the smallest to largest particle can have in the range greater than 10 to the power of 4 times, that is somewhere around 10,000 times. Now, let us look into a typical grain size distribution curves. If you look into the typical grain size distribution curves, we see that the percentage finer by mass which is represented on the y axis and the grain diameter on the x axis. Here you can see the larger particles and here you see the smaller particles. So, different curves are represented, indicate that different types of soils with the different compositions of the grains. So, this curve which is extending from left hand side to right hand side is named as well graded soil, and this curve represents uniformly graded soil. Uniformly graded soil or a poorly graded soil, that indicates that which is nothing but the soil is supposed to have a uniform size particles. Suppose if in a curve is such a way that if you get a kink here, something like this, there will be uniformly graded to some extent, and then there will be an absence of some certain particles, and this type of the curve is called gap graded or bimodal soil. So, the soil can be well graded, soil can be uniformly graded. So, this is an example for the desert soils where the soil grain particles are uniform in nature. So, idealized fuller packing, suppose if you have got a larger particles and the voids are filled with smaller particles of different sizes, then we say that this is an idealized fuller packing, where soil particles which is shown here is filled with the voids in between the soil particles are filled with grains of different sizes. This is actually indicates idealized fuller packing. Suppose if we have this type of fuller packing existing in the nature, then the grain size distribution will be something like this. So, this is called a fuller theoretical curve. So, what we have seen is the different types of soil combination can be possible, like it can be of well graded or uniformly graded or gap graded. So, having seen the sieve analysis for particles coarser than 75 micron, let us look into how to do a procedure for fine grained particle analysis, that is particles passing 75 micron. And we said that this analysis is required to be carried out if the percentage of the particles are more than 12%, that is the finer particles are percentage fines is more than 12%, then we are required to do this particular analysis, and this analysis is called sedimentation analysis. It is assumed that as a first approximation that fine grained soil particles can be idealized as small spheres. So, all the particles are idealized as small spheres. We knew that most of the fine grained soil particles, exceptionally leaving silt particles, clay particles, they are all plate shaped particles. In the sense, the plate shaped particles tends to have a plate shaped particles. They may be far from the spherical particles. That is one limitation in this particular method, but we will be discussing in detail in the due course of this lecture. So, as a first approximation, we assume that all the fine grained soil particles are idealized by small spheres, and spherical particle falling in a liquid of infinite extent, and all particles have the same unit weight. That means that we are assuming that the spherical particle is falling in a liquid of infinite extent and all particles have the same unit weight. And we are also assuming that particles reach constant terminal velocity within few seconds after it is allowed to fall. That means that the particles reach the constant terminal velocity within a few seconds after it is allowed to fall. So, as we are saying, although the clay particles are far from spherical, the application of basically the sedimentation analysis which is carried out by using Stokes law. The Stokes law is based on the equivalent diameters, provide a basis for arriving at the grain size distribution of the fine grained soils. This is a sufficiently realistic assumption to arrive at the fine grained soil percentage. So, let us look into how this sedimentation analysis procedure involves, the theory behind the sedimentation analysis. And as I said earlier, this particular sedimentation analysis is after Sir George Stokes 1891. According to Stokes law, the viscous drag force Fd on a spherical body moving through a laminar fluid at a steady state velocity V is given by Fd is equal to 3 pi mu Vd. That is, suppose if you have got an idealized spherical particle, that is equivalent spherical particle, the drag force surrounding the particle when it is settling in a laminar fluid is given by Fd is equal to 3 pi mu Vd, where mu is the velocity of the fluid, mu is the viscosity of the fluid, and V is the steady velocity of the body, and d is the diameter of the sphere, where mu is the viscosity of the fluid and V is the steady velocity of the body and d is the diameter of the sphere. So, once we get the drag force on the soil particle, let us see, if you drop a grain of soil into a viscous fluid, it eventually achieves a terminal velocity V, where there is a balance of forces between the viscous drag forces and gravity weight forces. The gravity weight forces in the sense, because it is in a fluid medium, the buoyant weight forces will come into picture. Suppose if you consider a falling particle with a steady velocity V, it has got the forces. One force is the drag force which is acting upwards, and the buoyant force which is the difference of the gravity weight force of the particle minus the buoyant weight. So, net force which is acting is Fg minus Fb. So, that can be determined, the buoyant weight can be determined, Fg minus Fb is equal to 1 by 6 into Gs minus 1 into gamma W pi d cube, where d is the diameter of the equivalent sphere, Gs is the specific gravity of the particle under consideration, gamma W is the unit weight of water. So, Fg minus Fb is given by 1 by 6 into Gs minus 1 into gamma W pi d cube. Now, from this we have got now from considering the equilibrium of the particle between the forces Fd which is acting upwards and net force which is the difference of the gravity force and due to the buoyant nature in a laminar fluid medium, which gives, once we take the vertical equilibrium, we will be able to derive the Stokes law, which is used for determining the particle sizes of the fine grained soil fraction. So, as discussed, For equilibrium of the soil grain, Fd is equal to Fg minus Fb. Fd is the vertical drag force and Fg minus Fb is the net force which is acting downwards on the soil particle which is idealized by a sphere. From this equation, when we solve for the equilibrium, the terminal velocity of the soil grain is obtained as V is equal to Gs minus 1 into gamma W by 18 mu d square. So, V is proportional to d square. So, this particular equation is named as Stokes law, and this is after Sir George Stokes 1891. So, this indicates, observe that V is proportional to square of the particle size. So, thus a larger a soil grain is, the faster it settles in water. This critical fact is used in the hydrometer analysis, which is the analysis which is used for determining the fine grained soil fraction to obtain the grain size distribution for fine grained soil. So, here what we derived is that by considering the equilibrium of the soil grain, we have derived and established Stokes law, which we said that V is equal to Gs minus 1 into gamma W by 18 mu d square. With this we said that V is proportional to d square, that means that the larger a soil grain is, faster it settles in water. This critical fact is used in the hydrometer analysis to obtain the grain size distribution for fine grained soil. Now let us look into the process of the sedimentation of the dispersed suspension. The theory of the sedimentation is based on the fact that the large particles in suspension in liquid settle more quickly than the small particles. Just now we discussed that V is proportional to d square, that indicates that the large particles tend to settle faster than smaller particles. Assuming that all particles have similar densities and shapes, assuming that all particles are idealized by the ideal small spheres and also have the ideally similar densities. If all particles were of a single size with effective diameter d, by knowing the terminal velocity we can calculate the time for the dispersion. Td is equal to 18 time for a with a particle size d, Td is given by 18 mu z into divided by Gs minus 1 gamma W d square. So, Td is equal to 18 mu z divided by Gs minus 1 gamma W d square. This is actually obtained from the Stokes law. So, the velocity which a falling particle reaches is known as the terminal velocity. That is what actually we have used a new terminology here, is that the velocity which a falling particle reaches is known the terminal velocity. So, let us consider here a jar having a soil suspension, that is a fine grained soil fraction is mixed with water, and let us assume that this is the suspension state at time t is equal to 0. The suspension is with the original concentration. Basically in the fine grained soil fraction, first it is required, before preparing the suspension, it is required to treat the soil, because there may be a possibility of having organic matter. So, to remove the organic matter, it has to be treated with H2O2 to oxidize the organic matter, and to create a dispersion of the soil particles, because we are interested in determining the particle to particle or a grain to grain size. So, to prevent this conglomeration of soil particles and to separate them, we use a dispersing agent. So, that once we treat the pre-treated soil and that is mixed with a known amount of water and made a suspension with in a known amount of volume of water. So, the suspension volume once is known. So, at time t is equal to 0, once it is left on the table or the laboratory desk, then this is the state at this particular point. Let us assume that Z is equal to 100 mm is the in a reference depth where we are trying to understand. After elapsing a time t is equal to Td, t is equal to Td, then what is happening is that you see at the top the clear liquid is shown here, and then below you will see a soil suspension still at the original concentration, and then some settled particles here. This indicates that the particles which are settled already coarser in size, then they are the particles which are moving around here, they are in finer in size and they take certain time to come for sedimentation. After a time t greater than Td, you see here the clear liquid range increases, and you see the increase in the deposition of the soil particles. So, at time t is equal to Td, the particles initially at the surface would settle past the depth Z is equal to 100 mm. At time t greater than Td, you see that increase in the soil particle deposition. So, this particular slide indicates that variation of the initial unit weight of the soil suspension at a particular depth, if you see that soil suspension is undergoing a change in the unit weight. Suppose if you are able to determine this change in the initial unit weight of the soil, change in the unit weight of the soil particle, then we will be able to arrive at the gradation of the fine grained soil particle, soil suspension. So, let us consider a suspension with the original concentration at time t is equal to 0, at time t is equal to 0, and this can be represented as a phase diagram with weight of solids and weight of water, and volume of water and volume of solids. The total volume is equal to Vw plus Vs is equal to 1, and weight of solids and weight of water is represented here. So, volume of solids can be written as Vs is equal to Ws by Gs gamma W, and volume of water which is equal to 1 minus Vs, and Vs we are written in terms of Vs by Gs gamma W, where Gs is the specific gravity of the soil under consideration. Vw is equal to 1 minus Ws by Gs gamma W. So, initial unit weight of a unit volume of suspension is given by gamma I is equal to gamma W plus Ws into Gs minus 1 by Gs. So, if you see into this term is the one which is actually changing the initial unit weight of the soil suspension, and which is more than the unit weight of the water. So, initial unit weight of a unit volume of a soil suspension is given by gamma I is equal to gamma W plus Ws into Gs minus 1 divided by Gs. Now, as the time elapses, let us assume that at time t is equal to Td at level say xx in that is at a depth z from the surface. If you are interested in determining the particle size, then that can be determined now in this slide here as shown here at level xx, which is a depth z units from the surface, top surface. The size d of the particles which have settled from the surface through the depth z in time Td is given as, that is from the Stokes law, we can determine d is equal to root over 18 mu Gs minus 1 gamma W into root over z by Td. So, z is the depth at which we are measuring this, and Td is the time at which this we are referring measuring the particle size d. So, it indicates that, note here we indicates that above the level xx no particle of size greater than d will be present. That means that all the particles which are coarser are already settled, and then only the particles which are finer is they are below this level xx. So, from the process of sedimentation of the dispersion, if the percentage of the weight of the particles finer than the d that is already sedimented to the original weight of the soil particles in the suspension is say n dash, then we can determine the weight of the solids per unit volume of suspension at depth z as n dash into W by V. So, here I have written n dash is W by V, which is nothing but Ws is equal to W by V. W is now treated as a weight of the solids in a known volume of unit volume. So, weight of the solids per unit volume of suspension at depth z is given by z is equal to n at depth z is given by n dash into W by V, where Ws is equal to W by V. So, unit weight of the suspension after elapsing time t can be determined at depth z as gamma z is equal to gamma W in plus n dash W by V into Gs minus 1 divided by Gs. So, from this rearranging the terms, we get the percentage final n dash as Gs by Gs minus 1 into gamma z minus gamma W into V by W. So, n dash is expressed in percentage. So, once by knowing the gamma z minus gamma W and then we will be able to determine the n dash that is the percentage finer. So, in order to arrive at this percentage finer, two different methods are generally in vogue. One is the pipette analysis and the other one is the hydrometer analysis. Out of this we will be discussing hydrometer analysis method for determining the percentage finer n dash. So, let us assume that for a soil suspension, that particles settling down right from the start, hence the unit weight of the soil suspension varies from the top to bottom. Consider that this is the soil suspension initially at time t is equal to 0, and once the particles tend to settle at time t1, this will be the status. As they increase in the time from the start of the test, you will see that the deposition of the soil particles in the at the bottom, and with this we will see that the particles are tend to settle with time. So, it takes a certain amount of time to undergo a change in the density from the initial state to the final state. So, this measurement of the density or the measurement of the soil, specific gravity of the soil suspension can be envisaged by a device called hydrometer at a known depth at a particular time provides a point on the grain size distribution curve. Suppose at this particular time here, this is an ideological representation of a hydrometer. The hydrometer is nothing but a device or a bulb which has got a stem and a bulb which is filled with lead particles, and it is graduated such a way that to give the specific gravity of the soil particle suspension. So, if at depth d1, then we are able to measure, that means that we are assessing the specific gravity at this particular depth, and you can see the increase in the height of this suspension after immersing this hydrometer. This is caused because of the the original height of the suspension increases because of the depth, because of the immersion of the hydrometer, that we discuss later to include this effect into consideration. So, measurement of a specific gravity of soil suspension at a known depth at a particular time provides a point on the grain size distribution curve. So, as we see here, gamma z can be written as GSS gamma W, that is GSS is the specific gravity of the soil suspension, that is gamma z by gamma W is nothing but gamma z is the at time t is equal to Td is the initial unit weight of the soil suspension at depth z after elapsing a time Td. So, the relation now gamma z is equal to GSS by gamma W, and which is equivalent to 1 plus RH by 1000 into gamma W. This RH is nothing but reading on the hydrometer, that will is a graduated readings on the hydrometer will be reading. Then GSS is nothing but the specific gravity of the soil suspension. Generally, the hydrometer is graduated with the following readings like 0.995 to 1.030. So, by rewriting now this previously derived expression, n dash is equal to Gs by Gs minus 1 into RH by 1000. So, here previously we have gamma z minus gamma W. After simplifying this by writing gamma z by gamma W is equal to GSS which is equivalent to 1 plus RH by 1000. So, gamma z by gamma W minus 1 is written like 1 plus RH by 1000 minus 1. So, finally, we will have RH by 1000 into V by W. For V is equal to 1000 Cc, then we can write n dash is equal to Gs by Gs minus 1 into RH by W. So, if we are able to measure the reading on the hydrometer and W is the weight of the solids, then we can determine n dash is equal to Gs by Gs minus 1 into RH by W, and Gs is the specific gravity of the soil solids. So, as I discussed, the hydrometer is required to be corrected for immersion correction, because generally this correction is required after immersing the hydrometer for more than 4 minutes. So, initially this correction is not required, but after 4 minutes, after elapsing a time of 4 minutes, this correction is required to be implemented. Let us consider that a jar and which is with a suspension. Then if you see here at this may be the reference depth, which is He, then we can say He here is determined here. After elapsing time Td, we can we can say that the increase in the height of the suspension is Vh by Aj, and at the center of the hydrometer, which is Vh by 2Aj. This is approximated that from the CG, if the weight of the hydrometer lies below the CG of this lies, weight of this is more than the weight of the stem, it is approximated that the raise of the hydrometer at the center, with reference to the center of gravity of the hydrometer is around VH by 2 Ag. VH is nothing but the volume of the hydrometer. Aj is the area of the cross section of the jar, which is approximated now at the mid height VH by 2 Aj. At the top here, at the stem level, it is VH by Aj. So this is the H is the height from the stem to the top surface, and H by 2 is the height from the CG to the neck of the bulb. So this is the before immersion of the hydrometer, this is after immersion of the hydrometer. Now He can be obtained now, it can be written as H plus H by 2, H plus H by 2 plus VH by 2 Ag minus VH by Ag is now referred as a He, that is nothing but H plus H by 2 minus VH by 2 Ag. This is after simplification, this reduces to like this. So once we get this, now we are required to convert the reading on the hydrometer into the effective height He. So that based on this effective height, we can substitute this effective height in the Stokes law to determine the particle size. So we said that the reading on the hydrometer is equal to GSS minus 1 into 1000, that is RH is equal to GSS minus 1 into 10 cube, and here a typical hydrometer is shown here. At the bottom of the bulb is filled with lead shots to give the vertical stability to the hydrometer, and the reading on the hydrometer graduates like RH is equal to 0, GSS is equal to 1, RH is equal to 30, GSS is equal to 1.030. With this, now He is the effective height. So for a typical hydrometer, it is required to determine the He1 and He2. This can be determined first by putting an hydrometer on a A4 size diagonally. Top and bottom of the hydrometer is noted, and then the neck is pointed out here. Then with this, we can determine the midpoint, that is the centroid of the hydrometer. So by arriving that He1 and He2, we can, and by using that RH as the reading on the hydrometer varies from GS is equal to 1, that is RH is equal to 0 to RH is equal to 30. With this, we will be able to estimate He is equal to He1 minus He2 divided by 30 into RH. This is basically applied for up to 4 minutes, and He is equal to He1 minus He2 by 30 into RH minus VH by RH minus VH by 2 Aj. This is due to immersion of the hydrometer connection. This is required to be made after 4 minutes. Once we get that, that means that once we measure RH and by correcting the immersion correction, we are converting that into effective height. From there, by substituting the Stokes law, we will be able to estimate the particle size at particular time. So now coming to this, whatever we have seen previously, the percentage finer N dash is equal to GS by GS minus 1 into R by W. This R now indicates that which is nothing but R is equal to RH plus Cm plus or minus Ct minus Cd, where Cm, Ct, Cd are the hydrometer corrections. Cm indicates hydrometer corrections for meniscus correction, and Ct indicates for temperature, correction for temperature, and Cd is the dispersion agent correction. And after incorporating these corrections, N dash can be obtained as N dash is equal to GS by GS minus 1 into R by W. That means that you are seeing here N dash is equal to GS by GS minus 1 into R by W, where R is equal to RH plus Cm plus or minus Ct minus Cd, where here once we getting this, N combined can be obtained as N dash into W75 by Wt. That means that W75 is the weight of the soil fraction passing 75 micron. Wt is the total weight of the soil taken for combined sieve analysis as well as hydrometer analysis. So that is the, from this we will be able to again from the, once we get the N dash, we can add these points to the sieve analysis curve. The points which are obtained from the sieve analysis or mechanical analysis can be added. Then what are these hydrometer corrections? They are Cm is the meniscus correction, because always this is positive, because the density readings are increases downwards and we will be measuring the lower reading. So, account for that, the Cm, the meniscus correction, and which is required to be applied, which is always positive. Temperature, the hydrometer is generally calibrated for temperature T is equal to 20 degrees centigrade. For T greater than 27 degrees centigrade, RH will be less than what it should be. For T less than 27 degrees centigrade, RH will be more than what it should be. RH will be more than what it should be. That is, Ct is equal to minus for the temperature correction is minus for temperature less than 27 degrees, because the reading on the hydrometer will be more than what it should be. So, to compensate for that, the correction has to be minus. And for temperature correction for hydrometer is positive for the temperature is greater than 27 degrees, that RH will be less than what it should be. And CD is always negative, because we add the dispersion agent like sodium carbonate or sodium hexametaphosphate to segregate the soil particles, so that we will be able to determine ideally the sizes of the finest particle sizes. So, we have seen that the Stokes law application for determining the fine grained soil fraction analysis, and we also said that the first and foremost assumption is that the platelet particles or the fine grained soil particles are idealized as a small spheres. So, as we knew that the soil particles are not truly spherical, they are far from the spherical. So, soil particles are not truly spherical, and the sedimentation is done in a jar, because it is assumed that the sedimentation process is undergoing in infinitely extent medium, but we are doing in a jar of limited dimensions. So, for D greater than 0.2 mm, that causes turbulence in water, and for D less than 0.0002 mm, the Brownian movement occurs. That means that bombardment of the particles, the two small velocities of settlement. So, this can be eliminated with less concentration. Even for the soils with the bentonite soil, it is advisable to take the percentage fine fraction, the soil percentage, soil solids percentage in the suspension is as small as possible. And there is also one more limitation, is that there may be a possibility of the flock formation. So, due to inadequate dispersion, though we pre-treat the soil, there may be a possibility that still the flock formation exists, and unequal specific gravity of the all particles and insignificant for the all soil particles with fine fraction. So, it is assumed that the specific gravity of the soil particles is constant. So, due to this there may be an error which may cause because of the unequal specific gravity of all particles, insignificant for soil particles with the fine fractions. To a great extent, these problems can be minimized to give the realistic results of the fine fraction analysis. By using this particular hydrometer analysis, we can assess the soil fractions realistically, so that we will be able to use and assess the estimate the fine soil particle sizes. In the next class, we will be looking into the gradation of the soil matrix and their use to determine determine and to classify the soils, and then we will also see the various physical states of fine grained soils with water.